Okay, we'll take a look at film screens and the relationship between the two of them. Now I'm recording this in my office, which means unfortunately it's possible that we're going to have interruptions and things like that. I will certainly try to minimize those things as best I possibly can. So this material here is really, in essence, what we're talking about is image acquisition from the analog side, where the devices that we're using is film, X-ray film, and intensifying screens. And the material for this is located in the Farber book, Chapter 6, pages 155 to 166. Okay, now, this assumes, of course, that I can actually move this thing forward. Come on, people. Oh, there we go. All right. Now, I just put this up here more, maybe I was traveling down memory lane here a little bit, but 1972, I was a first-year X-ray student, and no, I do not want to hear the cracks, but if I was doing, for example, a hand X-ray, I automatically put 100 mass up on the computer, on the generator, about 55 kV, things like that, and what I was utilizing was a piece of film in a paper envelope. There were no screens. The X-rays were directly exposing the film. It wasn't a particularly efficient system, hence the reason why we were using 100 mass. Now, having said that, I will tell you the detail was pretty exquisite. Okay? Now, how about if I was doing something much bigger, like a KUB or something like that? Under those circumstances, we used intensifying screens. The type of intensifying screens were called calcium tungstate. They were blue emitting. We might use 100 mass again, at about 75 kVp with these screens and a grid, reasonably small patient. Now, if you characterize that for what's kind of came on, I guess you would say at about 1976, thereabouts, there was an introduction to new types of intensifying screens that we called rare earth screens. These are specific materials that had not been used previously. They were much more efficient in the range of X-ray energies that we use. As a consequence, the amount of mass that you used with these new screens went down a lot, so that, for example, whereas I used 100 mass on a KUB, previous to that, I might use a quarter of that and still got good exposure, a good detail. And again, this was owing to the fact that you had a much more efficient use of the radiation by these screens. Kind of flip over here now, in the days of the digital world and things like that, as you probably know, 2 mass at about 60 is probably pretty decent for a hand. Remember now, part of this has to do with the fact that I would advocate using a higher kV. You might even perhaps make an argument that 2 mass is too much at 60 kV. Okay. On the other hand, if we go over to looking at a KUB, I don't know that things have changed terribly much from what they were with the advent of rare earth screens. 24 mass at 75 kbp is about average for a small, medium-sized patient. So on the screen side, things haven't changed all that much. Certainly, from rare earth screens, certainly things have changed a great deal if you're talking about extremities. Radiographic film is manufactured, kind of put together in a lot of ways just like photographic film. It is manufactured in a very, very dark environment because you don't want it to expose. It uses a lot of the same materials, silver-based and things like that. It comes in a variety of responsiveness, speeds, and also types. If you think about all the different ways you can have photographic film, understand that you can have radiographic film just like it. Okay? Keep in mind that photographic film is deliberately manufactured to be sensitive to specific ranges of light. And it doesn't have to be just white light. It could be ultraviolet. It could be infrared. The same way, radiographic film is also manufactured specifically to be either X-rays, not particularly great there, or frankly, light. Screen film is what is typically used today, and this is film that is deliberately manufactured to be sensitive to certain portions of the white light spectrum. Now, if you take white light and you put it through a prism, one of the things that happens is it breaks apart based on the wavelengths of the light. White light is not a specific wavelength. It is a range of wavelengths. As you can see here, everything from purple to blue to green to yellow to orange to red to magenta that are all combined together that actually forms white light. You can take film and manufacture it so that it likes or is more sensitive to specific portions of this light. And that's actually exactly what happens. What we then try to do is to match the sensitivity of the film to the color of the light emitted by the intensifying screens. So, for the most part, using screens and film together is the way we typically do things. It is possible to radiograph with film only, but that's actually very, very rare, and as I talked about, it's very, very inefficient. If you have a combination of film screen systems where you've got a cassette, under this circumstances, the film is used to acquire the image, the film is processed, the film is used for display, and ultimately you're going to store the film as the image. So do you remember I've talked about these little different areas here? Film is involved with all of it. Now, the film has to be there because the film is the medium that the image is actually going to be recorded on. But please keep in mind, okay, it is manufactured to go to where it can be sensitive to specific types of light. When we look at a piece of film, initially, just historically, the first X-rays, just like the first photographs, were taken on glass plates. That's the only medium they actually had. So they have this mixture, this emulsion, that they would literally roll onto these plates, and these plates would be used to expose the image and be manufactured that way. Glass plates are obviously rather fragile. So you imagine there aren't huge numbers of these radiographs left, but there are some. Okay, pretty clearly you couldn't keep up going that way. They went, as you can see here, at about 1918 to a base that was made of something called cellulose nitrate. Biggest problem with this one is it was highly flammable. As a consequence, X-ray film actually was a fire hazard that actually caused fires. It was very unstable. So yes, glass is inert. It's not going to burn up on you and things like that. But cellulose nitrate wasn't much of an answer, even if it was a little bit obviously more, I guess you say, more robust than glass. We've gone today to a film base that's made up of a polyester. Okay, and as I list here, very, very hard to tear. It is inflammable and it's structurally unstable. It is not going to deteriorate over time. It's not to say that the emulsion doesn't, but the film base itself does not. If you look at the way this cutaway is put there, the middle part there says the plastic base, and what that is actually referring to is the polyester base. Now, in addition to that, as you extend out, notice that there is emulsion, adhesive, and a protective layer on both sides. That's because screen film is double emulsion. That means there's stuff on either side here. And you can see how you've got the same things going on both sides. Okay, the polyester base, they added a blue dye to it. This is kind of a faint blue dye, and the whole point behind that was if you put a piece of film up there, let's say for example it was a 14 by 17, and you had collimated it tightly down for a thoracic spine, it would only take up a portion, okay, middle portion here for example, of the image. So then you would have all of this glare out here on the sides, and one of the things the blue dye was there was to reduce that glare. Big problem is that if you go from bright light to very dark to bright light to very dark, it gives you a really nasty eye strain, and wasn't very popular. Okay. So what you see today as a comparison between the two of them has to do with, in a lot of cases, the collimation. So with the digital image, for example, this is the collimator marks, where this was actually collimated to, but masking is applied, and the idea behind that masking is to do essentially what the blue dye did, which is to reduce the glare, because otherwise you'd have bright light coming through here and through here. Now here, what they've done is they've used a cylinder. You remember that here from the class. They've used a cylinder here to expose the area there of L5S1. There is going to be clear film here and here and along in here, okay? And that could contribute to glare and the problems that I was talking about eye strain. Okay, coming back again. So you have the polyester base, and it has a small blue dye. There is an adhesive put down so that you can have the emulsion actually directly adhere, stay tight with the base. This emulsion now essentially is a gelatin, okay, and it has silver halide crystals located within it. Okay, so this is just kind of like a mixture here. And what it does is it creates a crystal lattice work that the silver halide is actually kind of, I guess you say, embedded in it. Now, so this support medium kind of holds them in place. And what you want to do is to ensure that the emulsion is layered out on a nice, flat, even, so that you have the same amount of emulsion on one side of the film, for example, as you do on the other. Okay. The other thing is gelatin works really, really well because really it's kind of watery. So if you have wet processing chemicals, which is what you have for film, it's easy actually to go to work and get into the gelatin. The gelatin absorbs the water, and that enables you to saturate all the silver halide crystals, because that's actually where the action is. These silver halide, now the term halide is actually a chemical composition. Halide is part of the periodic chart. We're not going to go into that. But the majority of it is a silver bromide. A little of it is silver iodide. Okay, it's not super critical, but I just wanted to point out that this is the part that actually is going to respond to the radiation. It's not the gelatin, it's these crystals that are kind of embedded within your gelatin. Okay, now how this emulsion is manufactured. Okay, how big are the crystals? What is the distribution of the crystals? Do you have a lot of them? Do you have a few of them? Do we have emulsion on one side of the film only, of the base, or on both sides? All of these things are deliberately manipulated so that you can have different types of film. I mean, if you think about this, this is no different from photographic film. The speed of a film, and remember we've talked about the speed, it's the responsiveness of the system. Okay, the contrast that the film will give you, all right, the resolution that the film will give you is all dependent on how this emulsion is manufactured. Okay, so let's take a look. This is an example of silver halide crystals actually in film. Now, you know, you would probably look and think, well, we've got more halide crystals here, but I think the idea here is that smaller crystals will give you a more focused light, which means you should get a better image. In general, I think you will find that where imaging is concerned and resolution is involved, smaller is usually going to be better. Smaller crystals, smaller pixels, smaller thin film transistors, smaller everything will give you better resolution. So when you have your piece of film and the emulsion is on it and things like that, and all of this is done in a light, tight environment, it is put into a box which is also light tight, and it is opened up within a dark room, which is set up specifically to be the light that's in the dark room is not particularly responsive. Well, the film is not responsive to it. Okay, so you take your film, you put it in a cassette, which is a light tight environment. If you expose the film, whether it's to X-rays, frankly, or to visible light, right, a latent image is formed. A chemical process takes place that is not seen. If you look at the film doesn't look any different. Okay, but a chemical process has actually occurred. So in a sense, the term latent really means hidden. Okay, there's an invisible change that has occurred in the film that will only be manifested once you process it with wet chemicals. Okay, now This is what I'm going to go through here now is called the Gurney-Mott theory. This is the I guess you say working theory that we have as to how a latent image is formed. We're not going to go through huge detail. You just need to be familiar with it, okay? And I'm going through the steps here, but just relax. It's not that crazy. All right? You got a piece of film. Radiation of some time hits it. Now, radiation could be either X-ray radiation or it could be light. The bottom line is something hits a silver halide molecule, and the result of that is it ionizes. Okay, and that's essentially what you're kind of seeing here. The radiation is hitting, you have an ionization, so we now have an electron floating around out there, and we have a silver halide that is positively charged. Okay, all right. As a result of something like that, you're going to have the electron travel, and it's going to travel to a more positively charged sensitivity spec. In essence, they have doped this thing, if I can use that term, with an impurity that causes those electrons to be attracted to it. Okay? When that happens, the preponderance of these electrons, okay, are going to make it more negatively charged, okay, because they're attracted to it. And you can kind of see again what the heck is going on as you look through the images here. All right. Well, the positively charged silver, okay, from the halide is attracted to those electrons at the sensitivity spec. And as a consequence, the silver ions then kind of combine here, as you can see, and they kind of collect together, and it's the silver that forms the blackening on a piece of film. This all occurs because we do chemical processing. Okay, remember, you can't see this stuff happening, but this is what's actually going on. The metallic silver will be made visible, this kind of collection, after you've chemically processed it. And we're going to be spending more time talking about the chemical processing later. When we get into the processing part of things. Let's see if this is going to work for us here. Yay. Okay, here's the Gurney-Mott theorem here, and I'm going to just drop it, and I'm going to stop talking for just a minute. Watch what happened right there. First of all, let me go back and play it again. X-rays come in, cause ionizations. There's the little electrons that are basically attracted to the sensitivity spec. As a consequence, the silver atom, okay, it's actually a silver ion, okay, is in turn also attracted to the sensitivity spec, and it causes a collection of those silver atoms there, which is the blackening on the film. That's essentially how Gurney-Mott works. It's not that complicated. Just kind of follow it here. It sort of seems logical. Electrons. All right, then you've got your ions, and the ions in turn merge together to form silver, and the silver, of course, is the blackening portions there. So that's Gurney-Mott. That's what they think actually happens here. Now, the thing you have to understand is that this is occurring a lot. Okay, just because we've gone to work and changed a few ions is not going to mean that you're going to have much of a visible image. There has to be an extensive number of these interactions actually occurring here to actually produce the blackening on the film. Now, where you have no radiation, this process is not occurring. Okay, I want to keep that in mind. So you have both exposed silver halides, but you also have unexposed silver halides too. So we're going to have to deal with that part too, and that again happens during the chemical processing. Okay, so if we talk about the speed, the definition is the responsiveness of the emulsion, okay, either to X-rays or to light. And remember, for the most part, we're usually talking about light. Speed really equals the responsiveness. A lot of this relates to the idea of how efficient these systems actually are. Okay, so what are the things that would help contribute to the efficiency or contribute to the speed? Well, if you have lots and lots and lots of crystals, okay, it would stand to reason that you were going to get more reactions. If you had larger crystals, it would stand to reason that you're going to get more reactions. So overall, lots of crystals, let's say for example if you had double emulsion film, you would expect you would have a faster speed or faster responsiveness. Okay. Now, by definition, contrast where all this is concerned, we're talking about producing ranges of grays. We can manufacture film to be what we would call high contrast. What that essentially means is you're more likely to produce an image overall, all things being equal, that is more black-white, or you could have low contrast film that would have more grays. And also, I'm operating on the assumption here, if you get right down to it, that we're using a similar KVP. Okay. Now, the term latitude is there. Latitude means a margin of error for my purposes here. In essence, a low latitude, okay, means you have relatively fewer grays. For practical purposes, managing the exposure of these films is more difficult. That gets back to my margin of error thing here. On the other hand, a low contrast film that will have more grays would tend to have a wider latitude. You have a greater range of technical values that you can use and still get an acceptable image. Okay, so how do we figure all this stuff out and compare it and things like that? There is a mechanism, it's called sensitometry. And sensitometry is a representation of the different ranges of blackening that you could have on an image. And it's based, of course, on the exposure. Okay, now, what would be the differential with this? A penetrometer or step wedge, and you've seen these penetrometers before. They are of multiple thicknesses, is exposed so that you are going to have different degrees of attenuation based on the different steps. That image, that film, is then chemically processed and what you're going to do is produce an image that has a series of grays. So, this is kind of a bit extreme here, but you can see there is the step wedge, and you can see that you get the various levels of thickness. When the radiation strikes through, the least amount of radiation is going to come through the thickest part, which as you see here. The most amount of radiation is going to come through the thinnest part, here. Okay. Now, all right. This is graphical representation of essentially what I'm talking about here. Once you make the exposure, notice that we've got a range of grays. This is kind of the latitude. Okay. Now, what you're going to do is to utilize a device that's called a densitometer. That big blue device that is located in our, imaging area there, the lab, is a densitometer. And what you're going to do is you're going to measure the amount of light that is coming through at various points. And specifically this point, this point, this point, so on and so forth. And then you're going to plot those numbers on a graph. Okay? So, the area here that would be lightest would have the lowest value. The area here that is the darkest would have the highest value. The various here, it's not straight linear. As you can see here, it's rather kind of sigmoid. It's kind of curved. Okay? That shows you the responsiveness of this individual piece of film. And again, it's based on what happens here. So one of the things is different types of film will give you a different result down here once you go to work and produce the, take an x-ray of it. So again, radiation, you plot those different points. Here's an example of a couple more here. For example, what you are looking at is another sensitometry strip, and what you do is you measure these various and sundries here, and you plot the values. Now, I'll show you this in lab when we have a moment as to how these densitometers measure things. Suffice it to say, it is based on a logarithm, so that it doubles essentially in density every 0.3. Okay, so and that's kind of very similar to, if you get right down to it, Kodak imaging and things like that. So we create an area there, the sensitometry curve, okay, that essentially has a kind of a curved gradual area on the bottom. It's called the toe. Then we have the straight line portion where you've got consistent representation. It's kind of a consistent darkening as the exposure goes up, and then eventually that tapers off. At some point, you have full saturation. You can't make anything blacker than it already is, so this will taper off at that point. That's called the shoulder. Okay, so here's another picture here that kind of gives you an idea with the breakdown of what's going on here. Now, let me see, how am I doing here? All right, we are going to do that. The graph right here is showing you a number of different structures here. First of all, you're going to have on the x-axis the amount of radiation. So as the exposure is actually increasing, okay, and remember that's kind of based in essence on the what do you call it? Your step wedge. This is also showing you the degree of blackening over here, okay, that density. When you first do the manufacture, you're never going to measure zero, okay? First of all, keep in mind the film has that blue dye in it. That blue dye is going to absorb some light, so we're now at a non-zero state. At the same time, when they put the emulsion on the film, okay, there's going to be a certain amount of residual left. They might call it fog. It might happen during the manufacturing process. It might happen during the transporting process. It just might be old. What you're going to get then is what's called base plus fog, and that means we're going to be in a non-zero state here at the toe. It will never reach zero. All right, as the exposure starts going up, then you start having the responsiveness. With a piece of film, if you don't use enough radiation, okay, the density will be low. If you use more radiation, the density will increase. If you use too much radiation, then of course it's going to taper off. It's what we call the shoulder. Okay? In essence, what you're doing with something like this is that you're saying when it really starts responding. Okay? On the other hand, this part here is telling you the degree of contrast. In other words, the exposure goes up, but there's just this gradual increase. So what I've done on this next one here is just simply describe and define these terms that we just talked about. Okay? Now, as I just started to allude here, the position on the x-line shows the speed of the responsiveness in the system. The gradient, which is the slope, which is really along the y-axis, will show you the film contrast. Okay? Let's take a look. You've got here essentially intensity versus exposure. You've got two different lines here. The first one here is the more responsiveness or the faster speed film because it does everything with less radiation. Okay? The slower speed films requires more radiation to get a similar response. So let's say, for example, we want a density of 1.5 and you drag this across. I wonder if I can, from 1.5, you will get a response from fast film sooner, okay, than you will from slow film. As a consequence, you have to use more, okay, radiation to get the response from slow film than you do from fast film. Fast film, for example, we've already talked about speed, might be a 400 speed film. Slow film, what we talked about, might be, or at least slower, might be 200 speed. Okay? All right. Here's two more. If you compare these curves, okay, their position along the x-axis here tells you their responsiveness or the speed. Film A is faster than film B. Film A requires less radiation to get a response than film B does. So the speed of film A is greater as opposed to B. Same thing going here. These are a little bit different. How about the gradient? Now, the gradient is referring to how quickly it's going up along the y-axis here. Notice that A is moving up very, very quickly. It has a very, very, I guess you'd say, high gradient. This would be high contrast film. Okay? Now, and I'm just talking about gradient now, not position. If you compare A over here to E, this one here is going at an angle like this, whereas A is going straight up. The gradient between the two of them is different. Therefore, okay, you have a higher contrast film with A than you do with E. Now, I'm not saying that A isn't faster than E, because it is, okay? But the fact of the matter is that the contrast properties are different too. Okay, now the reason I put this in here is not so much that we're going to be talking about digital systems, but I wanted to kind of give you an appreciation of the difference between the two of them. If you look at this thing here, if we hit the analog system, there is your standard gradient right there. And this is called, remember, the sensitometry curve, otherwise known as the characteristic curve. And this is telling you the responsiveness based on exposure. Okay, we want exposure essentially in a proper area here. Clearly, E minus is not it. You're going to get underexposed here. This is the area where you'd like it to be because we're talking about radiation that's coming from here within the range, okay, of that slope of this particular film. This is overexposed and it's noticeable. This is grossly overexposed. So between the two of them, we can get a good image in this range of exposure and this range of exposure only. Okay? Now, with digital, notice that the gradient is so much wider. Okay? And the reason for that is that you can take X-rays among a lot of different areas here and still get a pretty decent image. So if you're way down here, you're going to get something, albeit noisy. This is optimal, okay? Notice that we got the kind of the range going here. This is a little bit overexposed, but the image doesn't look that bad, does it? Over here, it's obviously, this is super saturated. We don't want that. But this is the range that you can actually get a fairly decent image, okay? From here to here. Now, if I back this puppy up, oh, that's right. The good range is here to here. The latitude of a film screen system is lower than the latitude of a digital system. Okay? You can go to work and get away with more, as I've been telling you all along here, with the digital system that you can't get away with an analog system. Okay, changing subjects here just a little bit. Let's talk a little bit about spectral matching. And I've alluded to this just a little bit. We deliberately manufacture film to be sensitive to particular colors of light. And the colors of light are the ones that are emitted by intensifying screens. We have screens, for example, that emit green light. We have screens that emit kind of a purpley light. We have screens that emit blue light. So it's important that you match the screens, the film, with the screens. Because if you don't, okay, now you've got blue film that is waiting for, blue sensitive film that is waiting for blue light and it's getting green light. It's not very responsive. Okay, so keep in mind what the heck is going on with this. They have to be matched up in terms of colors. Now, I just found, and it's actually kind of hard to find pieces of unexposed film on the internet. So, but I found two here, one of which you see here has a blue emulsion and this one here has kind of a green emulsion. Okay, these things come from dyes that are put in here. Now, a dye is color, and what will happen is if you have that color, it will absorb any light that matches that color. Okay, so if you put something that's predominantly green, and you're going to basically not have to deal with the green portions of the spectrum, if I understand this all correctly, or blue for that matter. So they deliberately do this to change how the film responds to a particular portion of the light. Okay? So that kind of leads us to intensifying screens. Now I'm going to stop this right now, and because we've been going for a while here, and let's see where we go for this. I'll just call this part 2.